Hello, my name is Nathan Archambeau, and today I'll be discussing synthetic gecko feet and their applications on sticky tape. Specifically, I'll be doing experimental determination of their adhesive strength. Introduction. Geckos have a unique ability to climb walls due to millions of hair-like structures on their feet called setae. Synthetic setae have been created as an alternative to sticky tape, as they are strong and do not leave residue or imperfections on surfaces after being removed. Research at the University of Manchester found that gecko feet, or natural setae, create an adhesion of around 10 newton per centimeter squared. They made their own uh, gecko tape, which is made of polyamide microstructures. The structure of polyamide is seen in Figure 3. And the research suggests that polyamide tape has a very similar adhesion to gecko feet of around 10 newtons per centimeter squared. Their method of measuring adhesive strength was just measuring the maximum withstandable stress or force per area on the tape. The polyamide tape is available to consumers under the name Kapton tape. Research from the University of California, Santa Barbara synthesized tape using carbon nanotubes with a maximum shear stress of 36 newton per centimeter squared. It's important to note that it's shear stress, that is not the same maximum withstandable stress as found by the University of Manchester researchers. Carbon nanotube tape is available to consumers under the name nanotape. Okay, experiment. Measure the adhesive strength of polyamide tape and nanotape to compare those found in the literature. The method will be using this setup on the left, where I'll attach the tape to the glass and hang things from it to see how much weight it can hold. And the calculation will be find the maximum stress that the tape can hold by dividing the tension force over the amount of area in contact with the glass. Okay, here's my first attempt. So I used a metal gecko. It's painted metal, and I put little squares on each of the feet, and I stuck it to the piece of glass. I measured the area by measuring the length and width of these squares with my digital calipers. I increased the weight from 400 grams all the way up to 5.13 pounds, and it held it just fine. So I realized that I needed to go a little bit higher in mass, so I went to 10 pounds, and it was a big failure. So at 10 pounds, gecko fell from or unadhered from the tape, and you can see that in the bottom left. But it was important to note that the tape stuck onto the glass and it did not stick onto the metal, the painted metal. And this is evidence that it's not a good experiment to use this metal gecko. I need to use glass on glass contact to keep it relatively even between the two surfaces to make sure I'm measuring the tape, not the secondary material. Okay, my attempt two, I used 4 pieces of tape and held a 10-pound dumbbell from it, and I held it just fine. So this I don't want to go higher than 10 pounds with dropping a 10-pound dumbbell onto my counter. So I decided to reduce the area of the tape. So my second trial was 1 piece of tape in the middle. I held the 5.13 pounds fine, but when I added the 10-pound dumbbell, it started producing a bunch of bubbles, and you can see that in the right picture. Once all those bubble forms, very quickly the glass dropped from the setup. And so in trial 3, I used 2 pieces of tape on either side, and total they had a contact area of 4.58 centimeters squared. These failed after about 44 seconds. You can see this video here is on 5 times speed, and at about 44 seconds, it failed. So here is trial 4. 2 pieces of tape were used with a contact area of 5.65 centimeters squared, and this is kind of a boring video because with 10 times speed, it successfully held the tape. No bubbles were forming as seen visually, so I concluded that this area of tape could successfully hold 10 pounds. Trial 5, 2 pieces of tape were used with a contact area of 5.13 centimeters squared. This is a little bit less than trial 4. This failed after 3 minutes with 10 pounds. So it lasted for much, much longer than the other trial. And you can see in this video here that there's bubbles starting to form. You can see them starting to form from the corners and getting bigger from the middle. And then at about 3 minutes and 46 seconds, it failed. Okay, we'll move on to my polyamide tape test. So when I was testing the maximum stress associated with the polyamide tape, it wasn't consistent in which interface that it failed. So the polyamide type is single-sided, and to make it double-sided, I did like a loop, and it couldn't even hold the glass. So I figured I'd put nanotape in between 2 pieces of polyamide tape, the polyamide tape contacting the top glass plate and the bottom glass plate, as seen in figure 17. But we can see that there was a failure. You can see in figure 16, there was a failure between the polyamide tape and the nanotape and the polyamide tape and the bottom glass plate. I didn't want that. I needed to be able to see a clear indication that the polyamide tape couldn't adhere to the glass plate, not the nanotape adhering to the polyamide tape, because at that point I was just measuring the adherence between nanotape and polyamide tape. For this reason, I'm not going to report my findings from this due to experimental inconsistencies. Okay, glass contact nanotape results. Here we can see the equations I used. The force is just the mass times gravity as it's hanging, and the stress is the force over the contact area. So table 1, you can see the object masses. The glass plate was 0.62 kilograms, the dumbbell was 4.31 kilograms, and the miscellaneous water coins, nuts, and bolts were 2.33 kilograms. They all held the water coins, nuts, and bolts in the glass plate, so you can see mass held. They at least all have that. And then in our table 2, we have our non-failure trials. These trials were trials where the tape did not fail. So we could see that in trial 1, the maximum stress was 7.13, or the stress that it held was 7.13. Trial 4, the stress that it held was 9.28. Okay, in table 3, we have our failure trials, trial 2, 3, 5, and 6. I added an extra trial here just to get one more data point. You can see that in trial 5, which was the lowest, stress failed was 10.2, and this is just a little bit higher than the maximum non-failure trial, which is 9.28. So these are really the values that are important. So the maximum stress is probably somewhere between 9.28 and 10.23. All right, and here we can see the time to failure trials. I wanted to plot this because it showed something quite interesting. Theoretically, if you found the maximum stress, then the time to failure would reach or approach infinity. So we can see that the stress versus time to failure plot, that at around 9 or 10 newtons per centimeter squared, the graph starts to level out or reach an asymptote. So theoretically, if we had stresses even closer to the maximum, then this would reach all the way out into infinity. This is evidence to the fact that the maximum stress is somewhere between 9 and 10 newtons per centimeter squared. All right, the discussion and conclusion. This experiment suggests that nanotape has a maximum stress between 9 and 10 newtons per centimeter squared. The maximum stress is definitely lower than the 36 newton per centimeter shear stress reported by G et al., but this makes sense because the shear stress also takes into account friction as they are pulling the tape parallel instead of pulling it perpendicular. I found that nanotape exhibits a similar adhesive strength to polyamide tape and gecko feet, which are reported in the literature to withstand 10 newton per centimeter squared. And then to accurately test the polyamide tape, I need to get a double-sided version of the tape to use the same method as I used the test nanotape. Here are my references. Thank you so much for watching.